were displaying the different ways for how data can be displayed, we talked about measures of center and what that represented. We've got the mean, median, and mode as our forms of measures of center. Remember that mean and median can both be used to describe averages. So when we're talking about a test average or average height in a classroom, things of that sort, we focus on just the mean and or the median. If an outlier is present, an outlier represents a value that is very different from the rest of the data set. Either it's a lot bigger or a lot smaller than the rest of the data. Then that means that you should not use your mean. You should use the median only. The outlier makes the mean unreliable, so you have to use the median to represent your average. And that's where we left off. What we're going to talk about real quickly right now is measures of variability. Okay, so measures of center represented averages. Measures of variability are going to describe how spread out the data is. Okay, so let's write this down. Measures of variability. So when we talk about variability, we're focusing on, mathematically, we're looking at range and IQR, interquartile range. Okay, so the range and the interquartile range show the layout of the data. So we use measures of variability to describe how spread out or how compact the data set is. So if I tell you guys, like if I say, hey, everybody stand up and spread out, what does that mean I'm asking you to do? If I'm asking you to spread out, what do I want you to do? Anybody, come on, guys. This is a common term that you probably have had since elementary school. When they say, okay, guys, you're in the gym, spread out. What do they want you to do? Like stand around the room. Do they want you to stand side by side? No, they want you to be as far away from each other as you possibly can, right? So if I want you to spread out, I want you to be as distanced as possible from people. If I say I want it to be more compact, so how many of you have ever gone to like the aquarium or to the zoo or to the Infinite Energy Center? Okay, if you park in their parking lot, they actually have sections of their parking lot that said for compact cars only. A compact car. What is a compact car? Amir? Not a large car. It's a small car. A compact car means it's a very small car. So if we're saying it's for compact cars only, it's a small space. An SUV or a minivan or a truck cannot park there. It has to be for those smaller sedan kind of cars because it's for smaller spaces. Same thing with like motorcycle spaces. They're really small because a motorcycle's smaller, right? So compact means that it's more closely packed in together. It's not spread out. It's close to each other. So when we are using variability, we're describing either how spread out the data is or the reverse, how compact or close together. So I'll write compact and in parentheses, I'll write close together. That the data is. So a lot of times people think that when we're looking at data, that it's the only thing that's important is the average. But the average means nothing to us when it comes to data. One of the most important things is that variability, because knowing the variability will allow us to know whether the data set is a good predictor or not. If I'm looking at, Chantel, we'll say Chantel, she does her work, and her assignment, she gets a 98. Next one, she gets a 95. Next one, she gets a 90. The next one after that, she gets a 96. When I'm trying to predict how she's going to do on a test, do I have a good idea of how she's going to do with those kind of scores? Yeah, I have a good idea. Okay. Now let's say that I've got, let's say instead Chantel, instead of getting these 98s and 97, maybe she gets 52 and a 60 and a 55 and a 51. Do I still have a good idea of what she's going to do? Yeah, because those scores are all very close together. So I have a good idea that she's either going to do really well or she's not going to do well at all, because her scores all are close. They're compact. They're not spread out. They're good, reliable sources for predicting how she's going to do. But if Chantel's all over the place, oh, she gets a 55 on the first one, then she gets a 92 on the second one, and then she gets an 86 on the third one, and then she gets a 64 on the next one, and then a 12 on the next one, and then a 97. Do I know how she's going to do? No. She's unpredictable, because she's, okay, these are good, these are bad, these are medium, these are bad, these are good, these are bad. It's everywhere. So I have no clue how she'll do. So when data is spread out, it's not very reliable. It's not a good source of making a prediction. When the data is compact, when it's close together, it allows us to know whether, okay, is this information is going to be a good predictor or not. And guys, it's used all the time. I know I relay a lot of things back to COVID just because that's what's relevant right now. That's what you guys are experiencing. It's an unfortunate thing, but it is something very relevant. When we're using data about COVID, like right now, y'all can get vaccines, right? You're of the age group that can get vaccines. My daughter is of the age group that can get vaccines. My son is not. My son doesn't meet the cutoff. The cutoff right now is 5 and up. However, back in February, they were about ready to go ahead and give the vaccine to everybody who was under the age of 5. They were ready and set to do that until they started looking even more at the data and realized the data was too far spread out. It had too much variation to it that they couldn't use it as a reliable source to predict how many doses or how many shots did that group need. Some kids in the trial group only needed 1 dose, and that 1 dose stuck well with them. Some needed 2, some needed 3. Some, no matter how many doses they gave, it wasn't showing an efficient amount of boost or antibodies in it. So they had to go ahead and cancel and postpone. Well, then they said, okay, we're going to postpone it right now until our data can become a little bit more compact, shows less variety, so that we can make a better prediction about how much we're going to need. So then they said, okay, we're going to push it to April. Well, April is almost around the corner, and just 2 days ago, again, they said, hey, we're going to have to postpone it again because they're having issues with this group. So you have to have an understanding of not just averages and measures of center, measures of variability. If you've got too many unreliable, unpredictable features happening, then that's going to have a huge effect on your outcome. So you have to make sure that you understand how variety or variability comes into play. Very important thing, okay? Let's write this down too, because a lot of people get very confused. If I say that you've got a good average, then you're looking at a high mean, right? A high mean or a high median means that you've got a very good average, a high average. The higher those are, the higher your average is. The reverse is true for variability. You are looking at the opposite. If data is considered to be consistent, okay, in order for something to get approved, when we're talking about things like vaccines, you have to have consistent results. In order for the results to be considered consistent, then that means your variability, or in this case, what we would call the range, has to be small. So if you are wanting consistency, then you need a small range or a small interquartile range. And a lot of kids get that confused because they're so used to seeing, okay, if I want a good score on a test, that means I have to have a high average or a high mean or a high median. But in here, if I want a good variability, I want a good predictor, a reliable source, then I don't want something to be high. I want it to be low. The smaller the variability is, the more compact the data set is, which means you can make a good prediction from it. Again, if my grades are spread out all over the place, I don't have a reliable source of how I'm going to do. But if my grades are all consistent, they're all in the 70s, then I probably have a good idea of how I'm going to do. Or if they're all in the 90s, I have a good idea of how I'm going to do. Okay? You want data to be very compact. Please make sure you have this written down and put a star by it. It's important. Because again, this is the one that confuses people the most. And we're going to be coming back to this multiple times today. And if I call on you and ask you to repeat this statement, you need to make sure you have it somewhere in your notebook. Okay? When you are done copying that down, go ahead and flip to the next page, and we're going to draw one more graph, and then I'll hand you some handouts for us to answer some questions about. Does anybody need this still? Okay. All right, we're going to draw one more graph for a box and whisker plot, because we're going to talk about how you can identify or get an idea of mean from a box and whisker plot, even though we don't know what the actual mean will be. So draw a number line. All right, my number line is ranging from 5 all the way up to 60. And I'm going to draw 3 box and whisker plots on here. I'm going to draw 3 separate box and whisker plots. So I would recommend that you use a like some highlighters. I'm going to do them in 3 different colors, and these are the colors that I'm going to use. I'm going to use pink, blue, and green. I strongly recommend that you use those same colors so that you can distinguish between the box and whisker plot and the statement that I'm going to give you about it. If you don't have your own, then see if the person next to you will be ever so polite to let you borrow from them to use. I did not say to start talking. I don't believe that if you talk, then that means color is going to magically come out of your pencil. Quiet. You're copying. If you don't have it in color, then you're just going to have to label it. All right, go ahead and get these written down. If you don't have colors, then go ahead and just label the very top one A. Label the center one B. And label the third one C, the one closest to the bottom C. Get those labeled in. Make sure you've got them drawn. All right, let's go ahead and take a look at these. For the very first box and whisker plot A in pink, let's discuss the look of it, the symmetry of it. If you're looking at just this box and whisker plot, does it look symmetric to you? Symmetric meaning that if you were to look at the lower 50%, is it going to be resembling the upper 50%? So remember, 50% is going to be from the lowest point to the median. So is the look of the lowest point to the median the same as the median to the upper point? No, right? You've got a larger lower half and a smaller upper half, don't you? Okay, so it's not symmetric. So for box plot A, the pink plot has more of a spread or variability on the lower half. Okay, so the lower half of my data set is more spread out than the upper half of my data set. Would you guys agree with that? Okay, in a situation like that, when that occurs, even though we don't know exactly what the mean is, because again, to know the mean, you have to know what each of the data values are. I don't know how many numbers are in the data set. I don't know what the numbers are. All I know is that it has a small point of 5, a large value of 40, and there's a median of 30. That's all I know about my data set. I don't know any specific numbers beyond those. So the only thing that I can gauge about the mean is that it's actually going to be smaller or less than the median. That's the only thing that I know about the mean of the pink data set. That the mean is going to be smaller than the value for my median. So what is the median? What is the median for plot A? What is plot A's median equal? Nick? 30. If we're looking at the median, remember the median is this value right here, that line inside of the box. The line inside of the box is going to represent the median. So if I follow this line all the way down to my number line, it stops at the 30. So the median here is equal to 30. So again, I don't know what number the mean is, but I can say that the mean is a value that is less than 30. I know that because I have a lot more spread out data in the lower half of my data set than I do in the upper half. Okay? So even though I don't know the exact value of the mean, I do have an idea that the mean is going to be smaller than 30. All right, let's go on to the blue. The blue one, which is B, plot B. So looking at plot B, is plot B symmetric? Meaning, does the lower 50% look the same as the upper 50%? Yeah, right? This whisker is 10. This whisker is also 10. The inside of my box, I've got 10. And the inside of this part of the box is 10. So it's an equal distribution on both sides of the center. Okay, equally distributed on the left as it is on the right. So that makes it symmetric. So the blue plot, say that 5 times fast. The blue plot is symmetric. Okay, and when we're talking about symmetric data, it's really important to know that if you've got symmetric data, that means that the mean is going to be exactly equal to the median. So this is the only time This is the only time that we can tell what the mean is for a box and whisker plot. If your data is symmetric, then your median is going to be the exact same value as your mean. So I know in this case, the median, what is the median of the blue plot? What is the median of the blue plot? 25. The median, see here's my median line, my median equals 25. That means the mean is also going to equal 25. This is the only time that you can tell what the mean is on a box and whisker plot, only if it is symmetric. All right, let's take a look at the plot C, our green plot. Is the green plot symmetric? No, no. And in fact, it's the exact opposite of what the pink plot was. In the pink, we had a larger spread for the bottom half, but for plot C, the green plot, we have a larger spread on the upper half, which means it's going to be the exact opposite of here. With the lower half being larger, your mean was less than your median. But if the upper half is larger, your mean is going to be greater than your median. Okay? So write that down. The green plot, if the green plot has more spread, or variability as we called it, on the upper half, then that means that the mean is going to be greater, it's larger than the median. That's very important to understand. The mean is going to be greater than the median because of the fact that the upper half is more spread out. What is the median for the green plot? What does the median equal? 15. Okay, that line right here in the inside, it's 15. So the median equals 15, which means that the mean is going to be greater than 15. And I don't know exactly what it is, but at least I have an idea, a generalization of what it could be. And I'll zoom into this part a little bit more so you can see it easier. So what I gave you guys here is I gave you some comparative populations. Comparative populations means that when you have a representation of more than one group and you are trying to make observations or inferences, hence the reason that this unit is called inference unit, it's observations that you're making about several different population groups. In this situation, the first one is a box and whisker plot called a double box plot. Shh, quiet. With the double box plot, we're comparing the height of different basketball players from different teams. So again, we don't know specifically how tall certain teammates are, but we do have an idea of the variability for them. And we do have a somewhat of an idea about the average heights because we've got the medians that we can use to compare. So I'm just going to go ahead and write down a few questions that I want you to try and make an interpretation on. So go ahead and get these copied down. The first question I want to know is I want to know what is the difference. Okay, and don't forget difference means what operation, guys? Subtraction. Difference means to subtract. So what is the difference between the medians? Now on a test, it could be labeled as medians, but it also could be labeled as the average height. What is the difference between the average height? And again, if we're talking about averages, you're focusing either on mean or on median. We don't know what the mean is here, but we do know what the medians are. So they could call it medians, but they also could potentially be called average height. So you're going to answer that question. Then I want you to tell me, based off of what we just talked about with variability, which team's heights are more consistent. So you might want to relay back to what we first talked about today in class about consistency. What value are we going to use to measure consistency, and what do we want it to look like? And then my third question that I'm going to pose to you is just a straight calculation question. I want to know, what is the interquartile range for both teams? So take a moment, get those questions copied down, and answer them on your own. Okay, let's go ahead and talk about this. We've got two different teams, two different heights or different display of heights for the two different basketball teams. I want to know, what is the difference between the medians? So before I can find the difference, I have to know what are the medians for each of the teams. So who can raise their hand and tell me, what is the median height for the Knicks, for the New York Knicks? What is the median height? Denham? 80. Remember to find the median. So I'm going to talk about that again. When we're focusing on medians, we're focusing on the value inside of the box. The value inside of the box is going to be the median. So the Knicks, if I follow that down, is at 80. What about for the Nets? For the New Jersey Nets, what is the median for the Nets going to be? Angela? Huh? 79. So the Nets have a median height of 79. Now I need to find the difference. So what am I going to do with those two heights again? Subtract them. So all we're doing is 80 minus 79. And guys, what is that? 1. Okay, so the difference between the two medians is 1. All right. Consistency. We're talking about consistency. So again, if you refer back to your notes, when we're looking at variability or consistency, we want to look at what? What measure? Angel? Look how close they are, but what measurement shows how close or how spread out it is? Amir? Look back through your notes, guys. Julian, what? Go to the bottom of the very first page that we wrote on. Remember, I told you to star it. I said that it's important. What are we going to look at? The range. We're going to look at the range. And if we want it to be consistent, we want the range to be what? Small. If we want it to be consistent, we want the range to be small. So that's what we're looking for. We're looking for which team has the smallest range. We want to know which team has the smallest range. So range, guys, range starts at the smallest point and extends all the way to the largest point. That's the range. So I'm highlighting this in orange because I'm going to work this problem out in orange. I'm going to start at the smallest point for each of the teams and work my way to the largest point. So the range for the Knicks, my smallest point is at 74. My largest point is at 83. So I'm going to do 83 minus 74, and the range for the Knicks is 9. Then I'm going to find the range for the Nets. The smallest point for the Nets is at 72. The largest point is at 84. So I'm going to take 84 and subtract 72, and that's going to come out to 12. Okay, so the NICS has a range of 9. The NETS has a range of 12. Which one of them is more consistent? Amir? We want a small range. So which one has the NICS? The NICS have the smaller range. So make sure you write that fully out so that way you guys can remember. The NICS are more consistent because, and I'm going to put BC, you guys know BC is because, right? Okay, because it has a smaller range. That's what's important. The NICS are more consistent because the range is smaller. The NICS are more consistent because the range is smaller. All right, interquartile range. I'm going to highlight interquartile range, the word interquartile range in purple, because interquartile range is the size of the box, how big the box is. Okay? Shh, quiet down. We're talking about the size of the box for interquartile range. So let's focus first on the NICS. For the NICS, the box starts at 76 and ends at 81. So we're going to do 81 minus 76, and that gives us 5. So the interquartile range for the NICS is 5. Then we want to do it for the NETs. The NETs starts at 75, and it ends at 82. So we're going to take 82 minus 75, and that's going to equal 7. Okay, so those are our interquartile ranges. The interquartile ranges is going to be how large or how small the box is. Range is for the entire data. Interquartile range is just for that center 50%. Yes. What does what say? This? Under NICS. In the orange. NICS are more consistent because of smaller range. NICS are more consistent because of the smaller range. All right. Go ahead and answer these 3 questions. Okay, as I said before, you really shouldn't have to do any kind of calculation for this. It should be a pretty easy, straightforward problem. First, by identifying the following. Are these symmetric data? Like looking at Lily's, is Lily's a symmetric data set? Yes, it is. It has a nice equal distribution. It has a perfect bell curve. So if you're following along when we're talking about the symmetry, it has a perfect curve, meaning that from the center of the data set, it has a perfect curve going down, just like from the center to the right, it has a perfect curve going down. The center has 3 points. To the right and to the left, it has 2 points. And to the right and left of that, it has 1 point. Same thing for Alessandra's. Alessandra's also is a symmetric data set. It is perfectly curved. Okay, so it has an equal distribution to the left of the data set as it does to the right of the data set. An equal distribution. Gabriella, turn around. Okay, so yes, both girls or both sets are symmetric. And knowing the fact that both sets are symmetric makes it a lot easier when identifying the medians and then identifying the means without having to calculate anything at all. Both of them being symmetric makes it a lot easier because you don't even have to pick up a calculator. When you're trying to figure out the median of a symmetric data set, make sure you write the following down. If the data is symmetric, If the data is symmetric, then the median is directly in the center. So with that being said, knowing that these are symmetric data sets, and I said that the median is going to be directly in the center, what is the median going to be for Lily? What's the center value here? 60. Look at it. 60 is going to be the value that is in the center here. So Lily is going to have a median of 60. What is Alessandra's median going to be? 50. Her direct center is going to be at 50. So Alessandra is going to be equal to 50. And then as I stated before, again, if the data set is symmetric, then the mean is equal to the median. So that means that the mean for Lily is also 60, and the mean for Alessandra is also 50. You don't have to sit there and go, oh, okay, 40 plus 45 plus 45 plus 50 plus 50 plus 50 plus 55 plus 55 plus 60, add all that together and then divide it by 9. It's going to give you 50. That's what it's going to do. Because of the symmetry, the mean and the median are equal. Write that down so that you remember it. If the data is symmetric, mean will equal median. If the data is symmetric, the mean and the median will be the same. So that means Lily has a mean of 60 and Alessandra has a mean of 50. Okay, get that copied down.